All right, in this chapter, we're going to pull back the curtain and look at the hidden machinery of the web. We'll be exploring some really critical vulnerabilities that can lurk in the backend components of an application. You know, the parts of the system that you, as a user, never actually see. But you can bet attackers are always trying to find a way in.
It's really easy to think of a web app as just one single thing. But that's almost never the case. In reality, what you see on your screen, that's just the front door. Behind that door is a whole complex world, a gateway that connects you to this huge ecosystem of back-end systems. We're talking powerful databases, file systems, mail servers, other internal servers, the whole shebang.
So this leads to a pretty crucial question, right? What happens when an attacker manages to turn that very gateway into a weapon against your own systems? See, an application is built on this foundation of trust between all its different parts. Attackers are experts at exploiting that trust. They craft their input in a very specific way to trick the application into basically attacking itself, which can give them access to all sorts of sensitive data and powerful functions they should never have.
Okay, so here's our roadmap for this chapter. First, we'll talk about what this hidden attack surface really is. Then, we'll get into the nitty-gritty of some major attack types: command and code injection, file path traversal, and data protocol injection. After that, we'll touch on proxied and mail attacks. And to wrap it all up, we'll cover the core defenses you need to know to stop these things from happening.
All right, let's kick things off with the hidden attack surface. It's really important to get a good handle on this idea, because honestly, it's the foundation for everything else we're going to talk about.
Okay, so here's the absolute key idea. When data gets passed from one component to another, you have to remember that what's safe for the web app might be incredibly dangerous for the back-end system. Think of it like this. Different systems speak different languages. A string of text that looks totally harmless to the web app might contain special characters. We call them meta-characters that are actually powerful commands for something on the back end, like the server's operating system. And it's this fundamental misunderstanding, this mismatch in how the data is interpreted, that opens the door for almost every attack we're about to look at.
And that brings us perfectly to our first major category of attacks: command and code injection. This is all about an attacker taking advantage of that mismatch we just discussed. They craft their input to trick the application into running commands it was never ever supposed to run. Essentially, they turn the server into their own remote-controlled puppet.
So OS command injection is a classic. Imagine an application needs to run a simple command on the server's operating system, maybe to list the files in a specific directory. It takes some input from the user, say the directory name, and builds that command. But if the developer isn't super careful, an attacker can sneak in special characters, these meta-characters, that completely change what the command does. It's like slipping a secret note into the instruction, telling the server, hey, after you do that first thing, I want you to do this other thing for me.
And this is a perfect example of what that looks like. On the left, you see the application doing exactly what it's supposed to do. It's listing the contents of a directory. Totally normal. But look at the right. The attacker has injected a pipe character, that's the vertical bar, followed by cat/etc/passwd. Now, that pipe character is a special command for the operating system. It basically says, take whatever the first command does and feed it into a second command. And in this case, that second command dumps the system's password file right back to the attacker's screen. A tiny injection with a massive impact.
Now, if you think that's bad, dynamic code execution is even more direct and, frankly, more dangerous. See, some programming languages have these functions. PHP's eval is a famous example that can take a simple string of text and execute it as if it were actual code. So if an attacker can get their input into one of those functions, they're not just piggybacking on an existing command anymore. No, they are literally injecting their own code into the application as it's running. This gives them an incredible amount of power, pretty much the same level of control as the person who wrote the application in the first place.
Next up, let's talk about how attackers can escape their designated little corner of the server. This is called a file path traversal attack. Think of a web application as being in a sandbox. It's only supposed to play with files inside its own web root directory. Path traversal is the trick attackers use to climb out of that sandbox and start roaming around the server's entire file system.
And the weapon they use to do this is deceptively simple. It's the ... sequence, ... On pretty much any operating system you can think of, Windows, Linux, you name it, this is the universal command that means go up one directory.
It's a totally fundamental part of how file systems work, and that's exactly what makes it so powerful and so dangerous in the hands of an attacker.
So here's how a path traversal attack actually works. Let's say an application lets you view an image, and it expects a file name like myphoto.jpg. It takes that file name and joins it to a base directory, something like /var/ww/images. But what if an attacker, instead of a file name, provides something like /etc/password? The application, not knowing any better, just combines them. The final path becomes /var/ww/images//etc/password. The file system sees those // sequences and dutifully walks up the directory tree, out of the images folder, out of the ww folder, and all the way to the system's password file.
And here's a real-world example of what that looks like. You can see it right in the URL, that long string of traversal sequences. The attacker has successfully tricked the application. Instead of showing an image, it's displaying the contents of win.ini, which is a critical system configuration file on Windows. This is basically the smoking gun. It proves the attacker has broken free from the web directory and can now read pretty much any file they want on the server.
Now this is where it turns into a real cat and mouse game. Developers know about path traversal, right? So they write code to look for and block that // sequence. But attackers are clever. They have a whole bag of tricks to get around these filters. They can use different kinds of encoding, like URL encoding, to disguise the characters. It's like spelling out the forbidden sequence using a secret code the filter doesn't understand. And one of the sneakiest tricks is something called null byte termination. The attacker might provide a path that ends with a null byte character followed by .jpg. The application's security check sees the .jpg and thinks everything's fine, but when it passes the path to the file system sees the null byte as an end of string marker and just ignores the .jpg part completely.
All right, so far we've been talking about attacks that target the server's operating system or its file system. Now let's shift gears and look at attacks that target the actual data protocols themselves, the special languages that backend systems use to talk to each other. We're talking about things like XML and SOAP.
Okay, so let's zoom in on XML External Entity Injection, or XXE. XML is a super common format for exchanging data, and it has this feature called entities. You can think of them as variables or shortcuts. But here's the dangerous part. XML allows you to define an entity that pulls its value from an external source, like a file on the server's hard drive. So, in an XXE attack, the attacker crafts a special XML document. In that document, they define their own custom entity and point it to a sensitive local file. When the server's XML parser reads this document, it helpfully follows the instruction, goes and reads that sensitive file, and plugs its contents right into the XML.
This is a fantastic side-by-side comparison of how it works. On the left, you've got a perfectly normal, legitimate XML request. But look at the one on the right. See that doc type section that's been added at the top? That's the attacker's payload. It defines a new entity called XXE and tells the parser to get its value from the win.ini file. Then, down in the search term, they just call that entity using the ampersand and semicolon. So when the application processes this search and maybe echoes the search term back in the response, it doesn't just show and XXE. Nope, it shows the entire contents of that system file.
All right, for our final category of attacks, the perspective shifts a little bit. Here, the attacker isn't necessarily trying to steal data from the server. Instead, their goal is to trick the server into becoming their accomplice, to use it as a pivot point to attack other systems.
A really big one here is server-side HTTP redirection, or as it's more commonly known, server-side request forgery, SSRF. This happens when an application lets a user provide a URL, and then the application server goes and makes a request to that URL. The danger? An attacker can provide a URL pointing to a server on the internal network, one that's not exposed to the internet. Because the request is coming from the trusted application server, it often sails right past the firewall. This lets attackers scan internal networks and attack machines that they could never reach directly.
And here's another great example, this time with email. On the left, a totally normal feedback form. On the right, check out the email address field. The attacker has put in their own address, but then they added %0a and then a BCC header. Now that %0a is just a new line character in disguise. When the mail server is putting the email together, it sees that new line and thinks it's supposed to start a new header line. So it adds a blind carbon copy to the email, sending it to a whole list of other people. Just like that, a simple contact form has been turned into a spam can.
So, we've been through a lot of pretty nasty vulnerabilities here, right? We've seen how attackers can really mess with backend systems. The obvious next question is, how do we stop them? Let's wrap up by talking about the core defenses and best practices for building a much stronger backend.
The first thing to understand is that there's no single magic fix. You need a defense-in-depth strategy. So, number 1, use safe APIs. Whenever possible, avoid building command strings by hand. Your programming language or framework almost always provides built-in functions that are designed to handle these things safely. Use them. Number 2, whitelist your input. This is a huge one. Instead of trying to create a blacklist of all the bad characters, a game you will eventually lose, create a whitelist of the only characters you allow. If it's not on the list, reject it. Simple. Number 3, canonicalize your data. This just means you need to decode and simplify all input to its most basic form before you check it. This one move shuts down almost all of those clever encoding bypasses we talked about. 4, parameterize your queries. This is the core defense against all injection. It means using APIs that understand the difference between code and data. It's like telling the database, hey, this part is the command and this other part is just data from a user. Never ever treat the data like a command. And finally, number 5, sanitize and escape. For those times when you absolutely have to put user data into another context, like HTML or XML, you must properly encode it so all those special characters are treated as just plain old text.
And that really brings us to the final, most important thought I want to leave you with. If the input your application receives isn't just data, but could actually be a set of instructions, then who is really in control of your application? You or the attacker? The fundamental mindset shift for backend security is to treat all input, every single piece of it, as untrusted and potentially malicious. The moment you stop seeing user input as simple data and start seeing it as potential commands, that's the moment you begin to build truly secure application.